Good day. My name is Daniel Akilo, and today I'll be presenting my big data analytics project, which is on fine-grained Ballet action anticipation, and it is on an extension of the existing AnnChor dataset. And basically, this project represents an extension of the existing temporal action localization research into a new novel action anticipation research, focusing on classical ballet movements. And basically, the whole point of this system is just to demonstrate how we can predict the next ballet action before it occurs. And that's the task at hand. And this is my PowerPoint presentation. I'm just going to be taking you through. So basically, the task, and this is also our problem statement, is basically how can we predict the next ballet action before it occurs, and how we extend the existing temporal action localization to action anticipation by using video sequences to predict upcoming movements. And basically, the main challenge is extending this, as action anticipation is fundamentally different from action recognition, which identifies movements as they occur, or temporal localization, which was the original data set, and basically that finds when actions happen in videos. So basically, this specific task is that we need to learn from the current movement context to predict what the dancer will do next in the video. And basically, the key challenge here is that the ballet movements often have different transitions and phases, and the model must learn to recognize the early indicators to make accurate predictions. And basically, just the competition relevance, the action anticipation is an emergent computer vision challenge. And basically, the key challenge, as I just mentioned, is that these ballet type movements handle rapid transitions and movements as well. And then we move over to similar work. And basically, this is taken from the original AnnChor research, which is basically the AnnChor data set itself, which establishes a foundation for fine-grained ballet action detection. And it uses coarse fine networks and tri-det models, which achieved 11.09% mean average precision on AnnChor 260 subsets. So basically, this was very good, but however, most of the existing research that focuses on action recognition and temporal localization don't really speak about action anticipation. And basically, this is why most studies use short-term predictions as well. In terms of sequence modeling, the GRU architectures often provide effective temporal dependencies, and they're very good at data sets that for video understanding tasks as well. So this work just extends the foundation by applying techniques to the anticipation problem in the fine-grained domain space. And yeah, so basically, the data set properties that we have with this, the AnnChor dataset uses everything that the original does, and it provides a foundation for the research. So it has 1,020 high resolution ballet performance videos. I know it has 25,000 temporal annotations and 11 action classes. There are also different splits, so 816 training data videos and 204 test videos as well. There are 11 action classes, like I mentioned, just the different distinct ballet movements. So you have your Peru or your jeté or the other actions as well. And the features that I've implemented onto this dataset is basically getting the pre-extracted i3D RGB features, which the original does do as well. But with this, what I've done is just basically get 10 frames per sequence and 2,048 dimensions per frame. And it then gives the input tensors of shape, and the representation captures like temporal and spatial information for video sequences. And yeah, this is basically how that works. And then we now move on to the matrix, which is our evaluation framework. And basically what we've done is utilize top 1 and top 5 accuracy matrix. So top 1 accuracy is the correct prediction and the ground truth, whereas top 5 accuracy matrix is the ground truth within top 5 predictions. And the reason why I use top 5 predictions is so that instead of having one deterministic prediction, we can see predictions as in 5 other predictions of what the next move would be. And this I think is better in terms of analysis instead of giving one deterministic prediction as well. And then we also have per class accuracy as well, which some in terms of the data set, some actions occur more, which give better accuracy to that particular action as well. And so basically the first thing that we did was we trained the data set in 5 epochs, and basically epochs is basically just like one iteration throughout all the videos that we trained. And basically the first baseline model that we got was 57% accuracy, and we were trying to get 65% accuracy at least. I know ma'am in class said that it just has to be better than a flip of a coin, so that's what we did. And the methods and the model architecture that we've gone with. So basically the model architecture uses a 2-layer gated recurring unit, which is GRU, and it uses 512 hidden units in each layer. And the GRU is very good for sequential data because they can learn long-term dependencies as well. Our input is basically the i3D features, and it goes 10 by 2048 dimensions, and our output is just the probability distribution across the 11 actions. We also use in our training an Adam optimizer as well, which allows us to have a learning rate of 0.0005, and basically we then train the data set with 20 epochs. And the reason why we use 20 epochs is because to minimize and reduce overfitting, and as well so that we can we don't lose any training data as well. And then basically the system also implements FastAPI backend using ONNX model serving. ONNX is just good in terms of optimization, and we use Next.js and React for the front end for video upload and real-time predictions. And basically, in terms of our methods and our experimental design, what we've done is I did 3 experiments where the first one I just trained it with 20 epochs, and our baseline with 5 epochs was 57. And basically we improved that by extending the training time to 20 epochs, and we resulted in 66.32%, which is basically 9.32 improvement in our accuracy. And basically our experiment 2, what we did is instead of using 512 hidden units, we made a larger model, and basically that then uses 1024 hidden units, and basically this resulted in 66.22 accuracy, which is just a little bit off the accuracy that we got in experiment 1. And then our experiment 3, what we did is we lowered the learning rate from 0.001 to 0.0005, and basically that resulted in the best performance accuracy that we got, which was 66.88% over 20 epochs. So basically our GRU accuracy, what we got is the best one we got was 66.88%, and our transformer, which was another pipeline that we did to just compare, we got 52.57%, which used the same learning rate and also used the same amount of epochs as well. And for this task, GRU was just better. This was because, again, like I mentioned, GRU is better because it's well suited for sequential data tasks. And basically, yeah, the results that I just said, the best model accuracy was 66.88%. And it also gives us top 5 accuracy as well. And no overfitting was observed, and there was always consistent performance as well. System performance, the inference time was prediction is always quick, end-to-end processing. When you upload a video, 3 to 5 seconds, the video is uploaded and ready to be predicted. In terms of just deployment, we used ONNX, which reduced memory usage and as well as increased optimization as well. And efficiency of the system. And basically user interface, we use Next.js for a clean UI and real-time video playback as well. And you can also see the top 5 predictions with confidence score, which I will be showing you. And yeah, this is then those are all our results. And basically the key findings is that the model is 5 to 7 times better than random guessing, which gives us a meaningful predictive capability. GRU architectures are best suited for sequential data learning, and as well as optimization and lowering the learning rate is better for training duration and has a better impact than increasing the model size and stuff like that. So basically the system achieves practical deployment and a real-time performance as well. In conclusion, this project extends the AnnChor dataset and basically from temporal action localization to action anticipation. And basically it achieves 66.88% accuracy on fine-grained action prediction, and as well as we learned that the extended training duration and learning rate optimization is also crucial for performance as well. And the system also uses uncertainty awareness outputs, which is why we did the top 5 prediction, which gives us a more valuable information and analysis instead of one deterministic prediction. And yeah, future work can extend to learning and implementing enhanced generalization or multimodal features where we can implement music into prediction and other things like that as well. So this is the PowerPoint presentation, and now I'm going to be taking you through the actual system, which is the demo. And this is the demo, and basically what we have here, again, we just use Next.js for this, and basically this is just the interface and everything that you see here. This is the best accuracy that we got for the GRU, and basically we have the 11 action classes, and basically this is our input shape as well. These are the available actions that I got from one of the papers that's sent, and I just combined everything together, just making new actions as well. So basically we have the pipeline 1 and we have the pipeline 2. So basically how you can do this is I even put step-by-step here. You can upload a Ballet video, and then you can basically what happens is the backend extracts the i3D features, and then the model processes the video to understand movement patterns and predict the next action. And then you can also view the top 5 as well. So basically I'm just gonna do it here, and I'm just gonna select a video, which I'm gonna be using some of the original videos from the original AnnChor set. So basically we're gonna open a video and we're gonna upload a video, and then basically what happens is once we select the video, when we start playing the video, every 10 seconds a new predicted next action is predicted. So basically in the first 10 seconds a grand jeté is meant to happen, which is basically just a large leap through the air. So we will see that as we playing every 10 seconds, these top 1 accuracy and the top 5 predicted accuracy changes every 10 seconds. As you can see, we have confidence scores in what might happen next, and the reason why we have top 5 predictions is just if the grand jeté doesn't happen, then maybe the chaîné turn might happen or attitude might happen. So now basically what happens is we play the video, and as we play the video, you can see it says the grand jete was gonna perform. So we're looking out for a large leap through the air, and now we're looking for balancing extension. And as you can see, there are a few balancing extensions here. So the confidence of that was very high. That was 8, which is good. Now we have spinning turn on 1 foot, which is Perot, and as you can see, it predicted it correctly. There was a turn on 1 foot. And then next prediction was attitude, which is bent leg raised behind or in front. There's some bending going on, so I think that's how that was the prediction. But again, you can see the confidence is at 1, so the confidence is a bit low to know that the parade is gonna happen as well. Now we see that the balancing extension is 9.6, which is almost 10, and you can see it's happening as well. So the extended leg balance pose is happening, and that was a high confidence. And as we go in, it's just gonna keep on predicting as much as it can, and that is then the end of the video, and that's how we see the predictions come to life as well. And then we can also then change to our pipeline 2, which had like a 52.57% accuracy, and then we can select an individual real quick, and basically then we can see that the first action is a 1.59 confidence score. We'll see if that actually happens, and we're looking for a spinning turn on 1 foot, and we can see that this actually happens. There's a spinning turn on 1 foot, as you can see, and then the predictions just keep on going every 10 seconds. Obviously, just for time's sake, I'm gonna have to stop this in 30 seconds. But basically, the balancing extension, as you can see, it did happen there a little bit, but now it's back to Pere, and the confidence is a bit low, but it is still happening as well. And basically, that's basically just the gist of the whole system. We're able to upload a video and also just see the predicted action based on the videos, and what to look for, and the confidence score as well. We also see the top 5 predictions as well. And just swiftly, I'm just gonna move over to Google Colab training, and basically this is just a training process that I do. I see that my time is running out a little bit, so I'm just gonna move on swiftly. So here, basically what we did is I got access to the AnnChor dataset for the 10,020 videos, and I loaded the i3D features onto here as well. And basically the dataset analysis showed good distribution across training and testing sets as well. And basically the model architecture that I implemented a GRU with 512 hidden units, and basically GRU was chosen over LSTM for efficiency, and it was basically good for sequential data and sequential action anticipation, whilst capturing temporal dependencies as well. And basically what I did was I was able to use and process 10 time steps of 2048 dimensional features, which is what you see over here. And basically this then allows us to predict the next actions. So basically the training setup, we use the 80-20 train test split with Adam optimizer and a learning rate schedule as well. So basically this just allowed us to track both the losses and as well as the accuracy for when we were testing. And we also did 3 experiments as well. So the first experiment that we did, we trained it with 5 epochs, and basically the epochs are just the amount of iterations that we did throughout all the videos that we had access to. And basically the first 3 experiments that we did. The first one that we did, we extended the training time from 5 to 20 epochs, which gave us around 66.32 accuracy. And then our second experiment gave us, what we did was we did a larger model, which is 10,024 hidden units instead of 512, and we also got around 66% accuracy. But the best experiment that we did, which allowed us to have the best outcome and accuracy, was we lowered the learning rate from 0.001 to 0.005, and that's test 2. This is test 3, and basically with that, it gave us the best accurate score. As you can see here, we lowered the learning rate. It gave us the best accurate score, which was 66.88% accuracy, which is the best accuracy that we got. And we also tested a transformer model as well. But in this, basically what we got and what we achieved is that the GRU significantly outperformed it. And with this, for GRU, our accuracy was 66.88%, but for the transformer, we got around 52. Let me just show you here, 52.57%, showing that sequential processing aligns better with the GRU architecture for Ballet choreography. And basically, we then exported it to ONNX, and ONNX was good for deployment because it gave us better optimization and better performance in using CPU. And we also achieved 5 times better than random guessing as well. Moving over to swiftly to our code, and the code architecture is basically we're using Python, and we're also using Next.js as well. So we have our 3 backend files. Our model loader basically uses the action anticipation model class, and then basically it is the core inference engine, and it initializes the model and its info files parts, and it loads the ONNX model and the metadata, and basically it then reads the JSON files and contains the class names, the input shapes, and the accuracy scores for our data that we trained. And basically it then creates an ONNX runtime session which is optimized for CPU. And basically we now use a predict method over here, which basically handles the complete inference pipeline. It accepts the input validation, shape conversion, and then model execution, and then we then get the result, which processes the top predictions with confidence scores. So we get the top 1 prediction and the top 5 predictions, and that's basically what this model loader does. Basically it loads the model, and then we also get the top predictions with confidence scores. Moving over swiftly to our server, basically it uses a FastAPI, which provides REST API endpoints, and basically it initializes 2 global model variables for GRU and Transformer architectures, and basically it loads it from the dist folder over here. These are our exported models, and basically it then creates a visual processor instance, and it uses key endpoints. As you can see, it uses predict, and it also uses predict batch, and all these endpoints basically allows for complete video processing and allows us to analyze videos longer than 10 seconds. And basically the endpoints also allows us for file validations, and as well as HTTP exceptions and storage and feature extractions as well. So these API is used for our front end over here. So basically the front end just calls this back end API routes used for process validation and process video processing. And our video processor file, basically what this does is it handles the complete video to feature pipeline, and basically initializes the target frames 10, and as well as the feature dimensions of 20,048, and it matches the model requirements, and basically uses OpenCV, so CV2, to calculate the frame counts and the frames per second, and basically it allows us to sample across the video durations as well. I know the frames as well also processes 224 times 224 over here, 200 times 224, and basically also normalizes the pixel values from 0225 255 to 0 to 1 range. And basically what this video processor does is it uses NumPy as well to select the distributor frames and to ensure complete performance capture. So all in all, this video processor file just allows us to get the full length of the video, and so that we can have full prediction of the video because we have the full length of the video. And basically that's what our backend does, and our front end just calls in the backend and uses the data, the model info data, to just predict and upload the videos. So here we have our prediction display. It just shows us the top 5 predictions and the best prediction that we have. Our video player just it's the screen that we saw where it actually plays the video, and it also validates if our video is in the right format. And our video upload, basically this just happened, allows us to upload the video in the various formats and for validation as well. So basically all in all, the backend, basically the backend components work together, and the server over here receives the request, and the video processor basically extracts the feature, and the model loader runs the inference. And the system supports single video analysis and error handling, file validation, and the architecture supports and performs optimally, and the backend architecture allows for video inputs and delivery of accurate predictions, which we saw over here. And that is everything in the video. I know I did go ahead of the limited time that I had, but I hope the video made sense, and I hope you have a good day. Thank you.